Hi, and welcome to another one of our popular webinars on data center design optimization. My name is Paul Bemis. I'm going to be joined today by Scott Lewis, who is Vice President of Wireless Sensors, to talk about a project we've been working on together that combines sensor data with predictive CFD modeling using CoolSim. Before I get started, just a couple of housekeeping things. We've got the webinar set up in delivery-only mode in terms of audio, so you'll be able to hear what we have to say. If you have any issues with the delivery in terms of audio or video, in the GoToWebinar panel, there is a raise hand signal. You can put your hand up, and we'll try to help you. I'll try to help you. And the other thing is we're going to be taking questions using the question chat dialogue that's over in the GoToWebinar panel as well. We have found taking live questions can oftentimes be problematic with respect to audio, so it's better if you just type them out and ask us a question as we go along. We'll hit them all at the end. So Scott and I are going to try to get through quite a bit of material in the next 45 minutes. We'll save 15 minutes at the end for questions and really take it anywhere you want to go, including open up the microphones if in fact that turns out to work okay. So let me start the presentation today by just talking a little bit about who we are, Applied Math Modeling. Most of you know us, so I don't need to spend too much time here. But we are responsible for the development, the sales, and support of the CoolSim application. So CoolSim is a pretty well-known application. It is driven by the Ansys engine on the back end, so we're using the Fluent CFD solver and mesher and post-processor to drive CoolSim. CoolSim is really a interface, an easy-to-use interface for the specific task of modeling data centers. We deliver the solution using a software as a service model. We actually do all the heavy lifting associated with CFD on a big cluster, and therefore you're able to run multiple jobs concurrently and also run your jobs in parallel using multiple cores. This gives you very good cost effectivity, and as a result CoolSim is the most cost-effective solution of its kind in the market. We are all experts in the field of CFD modeling, development, and support. We are not data center experts per se, although we're getting a lot better at it, I must say. So now let me introduce Scott here and let Scott tell you about wireless sensors. Scott?
Hi everybody, thanks for joining us today. Wireless Sensors is, as you might expect from the name of the company, a wireless sensor company. We provide a suite of sensors primarily aimed at the data center. We have a unique technology which is particularly well suited for the data center environment. That is a frequency hopping spread spectrum semi-deterministic mesh network, and if that doesn't mean anything to you, that's okay. It just means that it works in the data center environment. Contrary to our name, we also do wired sensors, so we are more solution-centric than technology-centric. We want to provide environmental data for the data center market. And whether we need to use wires or not is sort of immaterial. So although primarily most of what we do is wireless because it is so much easier. Next slide. Thanks, Paul. These are some of our products. The first at the top there is the Services Gateway, which serves as a single point aggregator of all the data that we collect in the data center. We do have fairly thin application software running on that gateway, so it can act as a standalone unit. You don't need to plug it into anything else to make it work. You can actually show floor plans and have some rudimentary functionality just by itself. But then it connects to just about any DCIM or building management system, and of course provides data to programs like CoolSim, as we'll talk about today. There are a variety of sensors that go along with that. The one that is most unique for the data center is the multi-point temperature sensor, which you see there in black in the second row of products. And that daisy chains a bunch of a bunch of temperature sensors on Cat5 cable, so that they can be placed as far or near apart as you like. And then there are a bunch of other sensors that will look at things like humidity, differential pressure, current, contact closure, 4 to 20 milliamp input, or 0 to 10 volt input. So you could put a split core CT on a current a fan current wire and monitor the current going into that fan. And then the little Pelican case there on the bottom is an evaluation kit, which assembles an assortment of those products that would be appropriate to walking in one day to a data center, setting it up, taking some data, and then packing it up at the end of the day and walking out. One other aggregation of products we have is called a rack pack, which will populate with reasonable granularity about 1,000 square feet of data center, or 50 racks, depending on how they're laid out, of course. But that's sort of the starter kit and then the first application kit. The next slide is the gateway architecture. I mentioned that the gateway itself is a standalone device, and you can browse into that directly. Do a little bit of historization and graphing, a little bit of graphics where you load in a floor plan of your data center, and then you can see what's going on in a plan view, and then flip up a spot where you might have a problem and see the face of the rack that might show you some more data. And then, of course, that connects to the internet or to an internal system through a firewall or within a firewall, and all kinds of other applications. So that's kind of a brief overview of what it is that we do and how we do it. And in terms of this project, we're using a program that we ran with the Florida Atlantic University, funded by the National Science Foundation, and we were doing a number of things, trying to determine a bunch of parameters, and we're delighted to be able to share this stuff with CoolSim and see how it worked in a real life application. The next slide is just some pictures of the installation there at Florida State, or rather Florida Atlantic. The first picture on the upper left, I'm not sure that I can drive the cursor there, but Paul is
yeah, you can. Picture. You have control of it now, I think. Yeah.
Okay. That just shows the top of the servers, and there's not a lot of information from this picture other than the fact that it is a hot aisle containment system, and you can see the top of the hot aisle containment just past the first two flanges there. The next picture at the top in the middle is our gateway, just sitting up on top of a rack. It only needs power, and the one red Cat5 cable goes off to a laptop, which is browsing into it. So it's a pretty simple installation. There's no antennas, no mechanical mounting or anything required.
Where's its power source come from, Scott? Is that a battery?
Yeah, no, it's a wall wart. It's plugged in with a 5-volt wall wart.
Mm-hmm. Okay.
Comes with it. And then on the upper right is one of the sensors just stuck to the edge of a rack. On the lower left there is is one of those sensors, and coming out of it you can see a Cat5 cable on the bottom, and that is going to a daisy chain of temperature sensors, which is shown on the next picture. So the Cat5 cable comes in the top of the sensor, and another Cat5 goes out of the bottom, and those are daisy chained together, up to 8 per RF node. It's possible to do a few more than that, but we don't recommend it. The next picture is a temperature sensor mounted to the front door of a rack. And the next picture, the last picture, is one that shows the sensor actually inside the rack. This is unique because most wireless broadcasters won't broadcast from inside a rack very effectively, but we have pretty good success with that. So, so that's kind of unique.
Okay. So what we're going to do today, Scott and I are going to talk about the role of sensors in the data center and the role of CFD. Now, sensors provide a current state of operation. They can give you a tremendous amount of data about what's going on currently, and also alert operators of any changes in the current state that occur. But it is looking at past performance or current performance. It does allow you to do energy optimization because you can see the state of where things are right now and make adjustments accordingly to reduce energy consumption or improve cooling efficiency. The role of CFD in the data center is to predict what will happen based on changes. Sensors can't predict. They can only tell you where you are right now, what the current state is, what the state has been in the past, and any changes that have made over time. The role of CFD is the prediction component, the looking into the future, to do things like validate the initial design or predict optimal performance, or to study the effects of failure mode, which you can't do in a real live environment. So when you combine the sensor data with CFD modeling, you can use the sensors to not only get the current state of what's going on in the environment, but also can be used to set up the CFD model and validate the CFD model so you have confidence in its ability to predict what's going to happen in the future or under changed conditions. Furthermore, the CFD model can then be used to search for the optimal operating point, and then the sensors can be used to maintain that operating point, and that whole output can then be integrated into your favorite DCIM package. So that's an example, that's the process, that's how they work together, and that's what we're going to look at today. Now, just to review, I'm going to be using a couple of metrics here that you may not know or may know. If you've sat in on any of my webinars in the past, you will know these. The first one is the return temperature index. There are two ways to measure this one. The way we tend to do it in CFD is take a look at the rack flow rate, what is required by the rack or servers collectively, compared to what the air handler is delivering as a percentage. You want these to be equal. If the rack flow rate is too low compared to the air handler flow rate, you're going to get bypass airflow. It's going to come out of the handler and go right back into the handler without passing through the racks. Conversely, if the racks are too high compared to the air handler, or the air handler is too low, the racks are going to recirculate upon themselves. Now you can also come up with the same metrics using sensors by looking at the delta T's, the delta temperatures across the air handler compared to the rack delta T. It is the same thing, you're just looking at a different parameter. And so RTI is the first one that we always look at with respect to balance. Is the system balanced? Is the amount of air being delivered by the air handlers good enough, equal to, sufficient to handle the load that's put in place by the servers? And if not, how do we get there? The second metric we then look at is rack cooling index. Rack cooling index deals with the issue of compliance to the ASHRAE standard, the ASHRAE specifications for rack inlet temperature. Are the rack inlets compliant? Are they able to meet the upper high and the lower specification? And to what degree are they in compliance? Now, ideally, it would be 100%. You have none of them that are too hot, and none of them that are too cold. But also good would be 95% to 100%. As you begin to drop down to 90 and below, you've got problems. So we use this as one of the driving factors for optimization of a data center. What is the RCI quotient? It's a unitless measure. It's just looking at temperature over temperature and how many of the samples, of all the samples you've taken, how many of them are over or under the specification. So those are two metrics I'm going to be using today, together with PUE, but most of you know what that one is, so I'll use that one as well. And what we're going to use today for an example is a small data center, as Scott pointed out, that has already been instrumented with wireless sensor data, SensiNet data instrumentation. We're going to use measured data to set up the CoolSim model. We're going to then validate the CoolSim model. We're going to then use the CoolSim model to predict an optimal operating point and then adjust the cooling system to match that, and then would validate using the instrumentation. So this process here that we're defining is one that you should understand. If you're a data center operator, this is the way to get to minimum energy consumption and to keep your data center operating correctly. If you're a consulting engineer and you're looking to deliver services like this, it's important to follow the process as much as you possibly can. If you're not using a tool to model the environment at the moment, you should be, because it's a very important way to understand what the environment's going to do under various scenarios that you can't measure or experiment with any other way, either because you haven't built the environment yet or because you can't afford to turn cracks off and see what happens. It just isn't feasible. So this process is a fairly good one, we think. Now, Scott, you may want to just take a second to talk about this slide. This is sort of what you've got in the room, and you can go ahead and I believe you can drive the cursor at this point and sort of show us around if you like. Okay.
Sure. This is sort of a plan view of it's almost a schematic, I guess, of the data center that we're working with. The two racks, the rows of racks are here on the left, labeled left racks and right racks. Cursor doesn't seem to be following me, but you can see those two racks. And in the middle is a hot aisle. The two columns of numbers on either side of the racks indicate the sensors that are attached to that part of the rack. So the ones labeled hot are on the hot side of the rack, and the ones labeled cold are on the inlet side, of course. These temperature sensors in this case are connected, the two at the upper left-hand corner, which I'm pointing to. I don't know if you can see that I'm pointing to them, but on the upper left-hand corner. Thanks, Paul. Mm-hmm. They are connected to node 4. So that's an RF node that has two temperature sensors attached to them. The two below that are temperature and humidity sensors. And so there are some humidity sensors on the inlet and outlet side of that rack. I think those are the salient points of this picture. It's just to show the layout of the sensors in the data center.
Okay.
Well, by the way, one more thing. Can you just go back? Yeah. Yep. The cracks are actually in line here, so the blue areas are indicative of where the cracks are.
And they're APC in-row units, I believe, right?
Right.
Yep.
You can see we've got a fan input and a compressor input there. Those are actually sensors that were already installed that we've just picked up.
Okay.
Yep.
Now, here's the one of the first pieces of data that came out of the initial simulations. And the way this worked is I actually gave CoolSim to a colleague of Scott's at Wireless Sensors, and he went ahead and used CoolSim, built a model, and ran it. Now, he used a lot of the defaults in CoolSim, just set it up and ran it, and the amount of time it took him to do that was very short. You know, with CoolSim, you can build a model and have it running within the first hour you own the application. So it's very quick, very easy to use. It assumes a lot. It assumes some defaults. And what you can see here in this first plot, this is a slice. We're looking down at the data center. Here you have the nodes and the cooling units are here, and here are the nodes. It's a pod configuration, so it's hot in the center. The outer region is cold, and so the airflow goes out hot, out cold here, comes back around and gets pulled back through the servers and is hot on the other side. And the reason we put this plot up is that we wanted to show you that although the numbers are off right now because he's using a lot of default configuration, a lot of default data, the trend is actually correct. And the reason I point this out is there's a lot of debate about, you know, getting the CFD model nailed down to some absolute temperature or some absolute fine granular level of detail. And I want to point out to people that that you can always add more detail. Putting detail into a model is something you can do over time, you can continue to do. But my point is that even with the default settings, the trending is correct. And you have to remember that the best use of these kinds of tools are as an indicator to you, a guide to you as to what to do. They are not a forensic tool. They are a guideline to allow you to make good, informed engineering decisions. So you see here what we've got is, if you look at the results being predicted, and this is in ISO units at the moment, SI units, because that's what the application defaults to. You notice on the input side here, it's showing these numbers are measured data, and then what you see in color is predicted data by the simulation. So you see we've got 21, 22 degrees across here on the cold side. That's pretty close to what we're seeing with the simulator. But if you look on the hot side, not so much. Up here it's pretty good, 33, 35, not so bad. But as we get towards this end of the data center, the accuracy drops off. And you see that here predicting in probably 29, 30, and the measurement is 24, 25. Now the reason that's true is because the application, the CoolSim application, assumes a 20-degree delta across these servers, across these racks. And it oftentimes is not a 20-degree. As you can see, it's not a 20-degree delta. And the reason that's true is that when you produce an electronics package, the design engineers, and having been one myself, I can speak to this, you design it for max load. So you put a fan in there that's going to be able to take care of the maximum heat dissipated depending upon the configuration of the particular server that you are building. But then what happens is, of course, somebody buys the server and only configures it partially. So you've got a big fan and not a lot of heat load. So the delta T is low. And all you have to do is go back into the program, into the CoolSim application, and reset that. So to dial in the CFD model once it's built, you follow these steps. First, you look at the cooling units, whether they're cracks or craws or however you want to define them. They effectively are all the same to us. You set the supply to air temperature to exactly what is measured. So you go into the data center and you measure the supply air temp and use that as a boundary condition for the CoolSim cooling unit. Then you adjust the airflow to exactly what the measured values are as well. So you set the cooling units up to use supply air temp and flow rate as defined by what's there in the room. Then you go to the racks and you do the same thing. You set the rack heat loads based on estimates. And we are using average watts per rack in this particular model. You can get more granular than that and go to the server level if you want to, but I'd recommend that you don't go there if you don't need to. Remember, the best model is a simple model. The simpler you can make it, the faster it will run and the easier it will be to understand its output. So you can always make it more complex in the future, but the best model is a simple model that still captures the physics in the room. As long as you're capturing the dominant parameters in that room, which are generally flow rate and heat load and delta T, then you're in good shape and be able to use the tool confidently to predict any kind of case you want. So you set the rack heat loads based on estimates, and then you check the simulated output, return air temperature, and if they don't agree, you check the heat loads versus what's actually there, and then you take a look at the flow rates, and you just iterate until you get them correct. As long as you're within 10 or 15% of what's being measured, you're in fairly good shape, because remember, in CFD we're creating a mesh over the entire inlet or outlet of a surface. So for cooling unit, we've got sometimes 1,000, 2,000, sometimes more individual measurement points that we're doing calculations on. And when we calculate an average, it's an average across that 1,000 set of points on a given inlet or outlet. When you're using sensors, it's not the case. You can't afford to put 1,000 there. So please understand that the simulated and measured will always vary a little bit, just simply based on the way they're doing sampling and they're doing calculation. So the interface to make the changes is very simple. I just showed you a screenshot of it here in CoolSim. The expected delta T is always 20 because that's generally what the specification calls for in terms of max load temperature rise. So here I have the panel set up for a rack row at 4 kW with a 20-degree heat rise showing a flow rate of 618 CFM. So to adjust the model, you just look at what was measured, and we saw a measurement of 5, delta T of 5, heat load still 4, and you see the flow rate per rack automatically adjusts to 2475 CFM. And that's how you do it. You do it for each one of the racks. And this is a set of results that came from that run once we did the calibration. And what's kind of interesting here is that these temperature measurements line up quite nicely. Now, what I'm showing you is a complete set of output that comes from CoolSim. One of the nice things about CoolSim is you can export the entire output for a given run and put it into PowerPoint, as I've done here. This is a PowerPoint presentation with the entire set of results for a given run in it. So it allows you to bounce around and look at different cut planes and different parameters in the design without having to leave a single slide, in a sense. And so for each slide in a PowerPoint deck, you can have many, many, many variations of your design to show your customer or show colleague or what have you. But let's look at first the summary report. Here's the summary report. This is a text-based summary. It talks about the total heat removed from the room. It talks about total flow rate going through the cracks. Now you'll notice here that when we set this up to match what was being measured in the room, the total flow rate through the crack is only 10,000, where the total flow rate through the racks is 14,000. So as we scroll down, those should be balanced, by the way. So as we scroll down and take a look, the first thing I notice is that the return temperature index is 135. That should be 100%. This means that my racks are going to try to recirculate upon themselves because the flow rate coming from the cooling units isn't sufficient to meet their needs. Now, fortunately, I don't have any hot spots. My RCI high is at 100%, but my RCI low is at 96%, which means I've got some cold spots on those rack inlets as well. The other thing you can do with CoolSim is predict the energy consumption. Here we used measured data. We took a look at the amount of energy being consumed by the cooling units and plugged that into the program, and it's showing a PUE of 1.6. Not very good, as it turns out. And if we take a look at the crack performance report, we can see part of the reason that that is the case. Remember that these units should be delivering a delta T of 20 as well, and you can see they are not. They're ranging 14. Here I've got 16, 14 delta T, so those are low. The flow rates are shown here. These are actuals, and we have one unit that shut off, and it was shut off when we did these measurements, and so we wanted to calibrate the model, of course, by shutting it off in the model. But the total heat removed is really fairly low compared to what those units can handle. Those units can handle 25 kW apiece. And here we're only pulling 15, 16, 17 out of them, which means their efficiency from an energy point of view is going to be low. These units always get more efficient as the amount of heat rejected increases. I guess the other way to say that is there's a certain amount of overhead associated with driving them that is just plain there. But now if we take a look at the rack report, we see that the delta T's here are beginning to line up pretty nicely. I mean, I'm showing delta T's here of 5 and 4, just exactly, in fact, where we wanted them to be. So here's max, average, and minimum, and here we also look at whether or not it passed the ASHRAE recommended standard, and we pick out the high and highlight it in red. So this is a good review of what's gone on in the data center. It's a little hard to digest a bunch of numerical data, so we also provide it in terms of color. And these plots are relatively new. We've done these in CoolSim 4. Here what I've done is taken the range of acceptable temperature for rack inlet according to Class I server specifications, and I've made it green. And if you're too hot, then it's red, and if you're too cold, then it's blue. And you see, in general, this data center is conforming pretty well at its base level to the specification set by the ASHRAE standard, even though I've got an imbalance of airflow. And that's okay, but with only 3 cracks on, the question becomes, what's its performance in an N+1 kind of configuration? What if I lost the power to another crack? And furthermore, what's going on here with respect to performance? And you see here that these racks are trying to recirculate around themselves. There are a couple holes, fortunately, in in this system. There's a crack here above this one because the cooling unit is not quite as tall as the containment system, and there's also another one here at the end. And you can see the racks are blowing their air out and being fed back into themselves. They're recirculating. They have to because they have no other place to get their air. So I see a lot of people just moving to containment and assuming that that's the end of it because they've contained the hot or the cold. But in fact, there's a little more to it than that. You have to be sensitive about the pressure variations that are being caused or created in that contained area. You have to be sensitive to the airflows coming from the cooling units and the racks themselves. And most importantly, you have to test to find out what's going to happen under a failure mode condition where one of your cracks goes down for maintenance or one of your cracks in fact fails. Now, once we built the model, we took a look at the delta T's and compared to measured. And so here you see that I've got that same report coming out of CoolSim, and I've got the average supply temperature here. This is fixed. This is set by the user based on the sensor data. So that's fed right into there. The average return here is predicted. This is the simulated output driven by the CoolSim simulation system. And here's what the average return is as measured. And you see that I predicted 80 and measured 82, so we're at a variance of 3%. Same thing on racks. We did the same thing. Once we had the cracks in position, we went ahead and did the same thing for racks. And the measured outlet temperature is here, and the average exit temperature is here, and you see they're agreeing quite nicely. Again, you can spend a lot of time getting these things to agree perfectly. I find that if you're within 10 or 15%, then you've captured the dominant parameters in the room, and you can go ahead and use it to do effective prediction with the tool. So once the model is validated, you can then use it to predict what happens under various scenarios. For example, failure mode, or turning on the other crack, or adding more load to the room, or what's the optimal placement of the load. It can vary a great deal depending upon where you put it. You can use it for future modifications or enhancements. And each time you do that and put it in place, the sensors provide you the feedback to make sure that once you've got it in a position that you want it to be, it stays there. So we did a little modeling here to show you what happens if a crack fails. Now here, this one is broken apparently or not working. What if we lost the other one? Now we've only got 2 units. Now, if you look at this just from a pure numbers point of view, your conclusion might be that this will be fine because these are 25 kW units. And if you remember in my summary report, my total heat capacity, total heat load is about 49 kW. So you say, okay, I should be in pretty good shape. But what happens is the flow rate through the racks goes to 14.3. That actually improves things a little bit. But my RTI is sitting here now at 149. I still don't have nearly enough airflow coming through to satisfy the needs of these racks. If we look again, the racks, and they're both on full tilt right now, they're 4,800 apiece, but they only produce 9,600. So knowing the total cooling capacity isn't sufficient to be able to understand whether or not you've got a solid design. You have to also look at airflows, particularly in the case of containment, because unlike a natural convection room where racks can recirculate on themselves and at least be able to put some air across the electronic device, what happens here is if it's fully contained, you can't do that. The air won't come back around because it's blocked by the containment itself, and it'll starve. In this case, these would starve. Now, if you take a look at the total capacity, you see they are dumping nearly 25 kW apiece. They're working very, very hard. And their efficiency has actually improved a little bit. So they're now at 2.78. The PUE got a little better. But we've got all kinds of problems with recirculation, and this model would not run at all until I let some air out of that contained area. So I had to back off on some of the containment and allow it to leak a little before the flow rates would actually be strong enough to let this thing run. And you see on the cold side it's dumping as hard as it can, but it's not enough for the racks. So what happens is the racks start to recirculate on themselves, and that's what you see here is the opening up of the top that needs to be done and recirculate around the edge. So a failure mode condition in terms of operation of a data center is oftentimes very, very different than a steady state operation with everything running, all the cooling units contributing. And it's important to understand what these failure modes look like so that you have a plan in place of when a unit's going down for service or when a unit's going down because of a failure mode. You have an idea of what to do. In this case, what you'd have to do is run in and start pulling off the containment right away, or the service would starve. Now, in this particular model, let's take a look and see if they conformed, and they do. You see, if you pull the containment off the top here, then the model actually will conform to the ASHRAE spec and it will be okay. But you have to know that that's necessary. And you wouldn't know it if you didn't somehow run a model or study the detail a little bit more than is often done. The other one we took a look at was what if all four are running? Now when four are running, I've got the right amount of air coming into the system. So now if we take a look at our summary report, we'll see probably that our RTI is near 100%, because now we're giving the racks enough air, and so there's not going to be that issue associated with recirculation, both by the crack, bypass airflow, or by the racks. The RCI is here at 100%. That's looking quite good. We notice that the RCI low is at 74%. This tells us that the temperatures are a little cold on inlet. If we go to our recommended range, we see here that now we're a little cold. So we've got the airflow balanced a lot better, but we're running at a very low supply air temperature. If we take a look at our supply air temperature, we see that we're running in the 70, 60 degree range. That's fairly cold. You don't need to run that low. We do know through experience that raising this temperature, the supply air temperature, will improve the efficiency of cooling units, generally about 1% per degree F. The actual number is for every 1.8 degrees F, you get about 3.5% energy improvement out of the compressor itself, simply because it doesn't have to lift quite as hard to get to the supply air temperature that it's trying to get to. So that's looking pretty good in that particular design. And so the next step we went to was, all right, well, let's go ahead and raise the supply air temp and see how that behaves in terms of energy. And you see here that by doing that, we get a better PUE. PUE is now 1.6. So we're getting back to where we were in the first iteration, but with better RTI numbers. Look, they're all running at 100. So this design looks quite good. And if we take a look at our inlet temps, we find that they're all doing quite well. They're all green. If we take a look at any of the other parameters like recirculation from the racks, we're going to find it's minimal, as it is here. Everything's staying inside that contained area, and the system's behaving pretty well. So I simply lined those four scenarios up for you so that as viewers you could take a look and see what we've done here. And what we've done is we've started off with a coefficient of performance of 2.3. By the way, coefficient of performance is simply a ratio of the amount of heat rejected to the outside of the room compared to the amount of energy required to reject it. So, for example, a chilled water system, usually an efficient chilled water system will have a COP of roughly 4. It takes about a kilowatt of mechanical energy to dump 4 kilowatts of heat out of the room. DX units can do that as well. If their delta T's are high enough, they can do it as well. There's no reason why they can't, but they generally don't. Generally, DX units are run at very high fan speeds to keep the coils from freezing, and as a result, the delta T's aren't very good, and the energy efficiency of them is not very good, as compared to, for example, chilled water. So you see we started off with 2.3 here, and then we went to 2.78 as we turned C4 off. we had to use a lot more energy on those other two units. But the COP actually increased and the PUE dropped. So that was a net win. The problem with this particular design was not energy. The energy was looking good here. The problem was the RTI went to 149, which means the racks were recirculating terribly. There wasn't enough air coming out of the crack units to satisfy the needs of the racks. We turned all the cracks back on, and unfortunately we dropped to 1.96. The PUE got to 1.7, but things started to improve. In fact, it was running a little cold. So then the final thing we did was to increase supply air temp, which went to 2.28, and that gave us a PUE of 1.6, just about where we started. But now we have a good relationship between air coming out of the cooling units compared to air being required by the racks, and also the temperatures are in line as well. So this particular design in the early stages wasn't that far off, but that shouldn't surprise us, Scott, because it had containment in it, and it had been designed to be efficient, I think, as a pod. But again, we were able to iterate to get it to a more optimal design once we validated the CFD run. So I think, again, it shows that using the two in combination is a very, very nice way to go. Using the SensorNet measuring devices allows you to understand what the current state is and allows you to validate a model so that you can drive to an optimal state that you may not know where that is yet. And then it allows you also to understand, once the model's built, conditions such as failure, adding load, predicting what happens under certain conditions. And then again, using the sensors to measure what's going on in the room such that when it becomes suboptimal, you can again get out in front of it and see what's going on. And I believe you have some software under development here in that area. Is that correct?
That's right. So as interesting and exciting as what we've just talked about is, we also had another purpose here with this project at Florida Atlantic, and that was to prove out a set of software that from these graphs doesn't look maybe too exciting, but the really exciting thing is that these graphs show the response to a I'll call a problem in the data center without ever having to establish a threshold. So these three lines across the top, or 4 or 5 lines, I guess, are temperature measurements, and those are sort of normal state. Again, am I able to control the cursor here?
You should be able to. Whoops, sorry.
It doesn't look like I am, but up here in the upper left-hand corner, there you go. Thank you, Paul. Mm-hmm. Those are normal state temperatures, and then we started pulling blanking panels off a few of the racks, and of course some of the temperatures started to rise. That was identified by this software that we're working on as an abnormal state, and there's a green line that takes a dive here in the second chart, is indicative of the fact that, well, something abnormal happened. And I am 100% sure that something abnormal is happening, and so it is a very straight line that goes all the way to the end. Mm-hmm. The graph on the bottom says that, oh, this new state is, well, I identify that new state, and we can associate that state with the removal of the number of blanking panels that we removed. And the system then has learned that. It says, well, this is the new state. It's abnormal, perhaps, by looking at the second graph, but it is identified as this particular state. So you can identify a number of states that that you can simulate or you can preload, and say, when I see any of these states, I'm going to sound an alarm. So that's the fact that you don't have to set a threshold, you don't have to identify all the states that you're going to be looking for, the software is smart enough to be able to say, hey, something is going on, you better go look. And when that something can be identified, then you can actually load that in and say that this is a new state, I know what that is. So you can show that. But if it's a completely off-the-wall kind of thing that you've never seen before, you're going to get an alarm for it. And you can go and look at that. So I think that's a fairly powerful piece of analytics that can be added to the data that is collected here. One of the questions was, sort of there's a lot of data coming out of here. What can I do with it? It's a very, very good question because Paul has indicated some very valuable things that you can do with it in terms of calibrating a computational fluid dynamics model. And there are a number of other things you can do with it. It's kind of an embarrassment of riches sometimes, but there are lots of easy things that you can do by looking at some pictures.
Mm-hmm. So what we'd like to do now is open it up for questions, take any questions you may have. We have both put our contact information here. It is about 1:15. We hope to go 45 minutes and then open it up for questions. If you'd like to ask questions, please use the panel over on the right that comes with this GoToWebinar session, and Scott and I will try to answer as many as we possibly can. The first one coming in, I'll kick over to you, Scott, because it has to do with security of Wire's solution. How is that addressed?
Yeah, thanks, Mike. It was Mike that asked the question, I guess. When the military or the NSA wants to transmit things wirelessly and not have other people hear it, they use one of the techniques they use is frequency hopping spread spectrum, and that's what we use too. We don't use it for that reason, but it provides very, very good security of the data. I guess the first question to ask is why would anybody be interested in what the temperature of your racks would be, but just in case there's somebody parked outside war driving and tapping into your network, they would not be able to follow the hopping frequencies to the same dance that we perform. So it's a pretty high level of security.
A second question to you as well. Since they generate quite a bit of data, how do you handle that data? Do you need something like JMP to analyze the data?
Yeah. So as I said earlier, there's a lot of things you can do with this data. The first thing that you can do is just show it on a floor plan. And in our gateway, you can show red if you've got a hot temperature and blue if you've got a cold temperature. And things like rack cooling index are particularly valuable to boil down the data so that you're not looking at a whole bunch of temperatures. You're looking at where there's a problem. So we actually have incorporated that in the gateway, and you've heard a little bit about it in the model as well, where it allows you to see whether something is too hot or too cold at a glance, and then you can drill down and look at the supporting data a little more closely.
Another question to you has to do with location of deployment. How important is it, and how do you know where to put them?
Yeah, and that is a good question. We get into that dance quite often. How many do I need? Well, how many do you want? And so we kind of try to break that cycle with what I introduced early on, which is the rack pack. And we say, place to start is to instrument the top, the bottom, and the middle of every third rack. And then we'll put a couple of temperature and humidity sensors in the hot aisle if it's a hot aisle configuration, and then an inlet and an outlet on each crack. And that constitutes one rack pack. It's a place to start, and you get instrumented like that. You get valuable data with that kind of granularity. If you feel like that's not enough, you can always add sensors. If you feel like that's too much, then you can spread them out a little bit, and that might cover a lot more than 1,000 square feet.
Yep.
So there's not a set answer to that. It is we've kind of determined that most people find that top, bottom, and middle every third rack to be a good place to start. But use a lot more granularity than that.
A question for me, I believe, has to do with the number of iterations I ran and can it be automated. I ran probably 6 different iterations. The iteration time was quite short. I mean, the iterations only took about 10 minutes to run, so actually running iterations was not difficult to do in terms of time. And can they be automated? Well, they will be automated at some point. I mean, the whole idea of iteration of a CFD is to be able to do this quickly, do this in an optimized way using an optimizer. At the moment, we don't have an optimizer hooked up. Remember that with an optimizer, it takes a lot more compute cycles to get the job done. So, it's coming. We will get there. But at the moment, the iterations are done by hand, where there's a human in the loop. You set up a model, you run it. You set up another model, you run it again. The good news about the way that we've done CoolSim is you can do them concurrently. So you can do a sweep. You can say, I want to run it at supply air temperature of 60 degrees F, 65 degrees F, 70 degrees F, and 80 degrees F, and just keep setting up and kicking off those jobs concurrently, and they'll all run at once, and they'll all come back at once because they're running on a parallel system. So that's a fairly straightforward and fairly reasonable thing to do. It says here, why are we only using rack cooling units? What is the source of the outside air as required by the mechanical code? Not sure. These data centers are self-contained systems, so the air stays in the room. They're closed loop. They come out of the racks, and then they go back into the cooling units, and then back out of the cooling units into the racks. The other question?
The room actually did have some other cooling capability outside of just room cooling capability, so that's where external air would have been available. Those units were turned off for these tests, and I suspect they're turned off more often than not.
Yep. If you're using chilled water, how would you add a supplemental heat removal device, such as a closed-loop circuit cooling tower? Just add it outside. To us inside the room, all we're interested in is cold air supply temp. That's it, and airflow. So the whole issue of how do you get cold air is outside of the simulation itself. The boundary condition is what is the supply air temp. So regardless of whether it's an economizer you're using, or if you're using a DX unit, or you're using a CRA, a computer room air handler, chilled water doesn't matter, swamp cooler doesn't matter, because all that is important to the simulation is the airflow. What is the flow rate of the air coming into the cooling system or from the cooling system, and the other component, of course, is supply air temperature. From then on, you can do everything else. You can simulate variable speed fans. You can simulate changes in delta T. You can do anything you like. Question here, I think, for both of us, Scott. If someone wanted to do a one-time analysis of their data center, would you use the Pelican kit or just manual measurements? And I think this lends itself to this discussion you and I are having about putting these two things together, the kit and CoolSim. I think
it would be very, very challenging to do it with manual measurements.
Yes.
And get them all concurrent.
But what we are willing to do, and this one came from, I think, Michael Davis, what we are willing to do is, if any of you in the audience are interested in having us do this kind of analysis for you, or if you're a service provider, a consulting company that provides data center assessment and consulting, and would like us to teach you how to do it, we're certainly willing to do that. We are willing to do either the work ourselves or work with a partner to do the work at, I think, very reasonable prices. Our goal, both of our goals, is to try to get this kind of work done at a reasonable cost so that it doesn't break the bank every time you want to run a simulation or you want to do some measurement of your data center. We think it's important. We're trying to drive down the cost of ownership of this kind of stuff, and I think you'll find us both to be very reasonable with respect to the cost parameter should you want to reach out and have us do some of that work for you.
That's right. We can walk in with that Pelican case, set up some measurements, and within a couple of hours be packed up and out of there. So it's a very quick, easy way to do it. Or we can ship you the Pelican case with some instructions. You can set it up yourself.
How many sensors per cabinet? You already mentioned that already, Scott. It's really 3, high, medium, and low, and as many cabinets as you can. You said every other or every third, I think, right, to begin with?
Yep.
Battery life of the temperature sensor?
We talk in terms of years. It's 2 or 3 years, depending on how many sensors you have and daisy chained from it, and how many what the reporting frequency is. We nominally report every minute, but in data center applications, 3 minutes, 5 minutes are not uncommon, and so you get a concomitant increase in battery life as you change the reporting interval. Just as a data point, if you had 3 sensors at a 1 minute reporting interval, 2 years is a normal battery life you'd expect.
Another question here about how do you know the numbers are adequate, and how do you correlate the airflow? How do you correlate? Again, the question of correlation. To correlate airflow, you can use bolometers and measure it. You can use delta T's as long as you know the heat load. So the 3 parameters are, flow rate, delta T, and heat load, right? Because heat load is equal to mass flow rate times density times delta T. So you have to know something, or you have to assume something, and then iterate on the others in order to get to where you want to go. So there's a balancing act here between spending a bunch of human labor collecting data and building models compared to the cost efficiency of taking a few samples together with a CFD model and approximating as best you can what's going on in that room, and you do it by sampling and checking and sampling and checking, and that's so we find it's not too bad. It's not too hard to get there. The models line up pretty well, pretty quickly, and remember, this stuff's been used in aerospace and automotive now for many, many years. So there's a lot of history associated with accurately predicting fluid flow, particularly this type, because it's relatively simple, straightforward fluid flow, heat transfer kind of stuff. So we can simulate it with very good accuracy through vented tiles or through vents or ducts or diffusers, but that's based on history and us adjusting those parameters so that they match quite well. And yes, one comment was economizer changes the PUE. Yes, of course. Economizer changes the COP. If you open the window and don't use any cooling unit, you've got a COP of infinity, right? So, but it's unusual that you're using an economizer to that effect. We do see it. I mean, you've seen some of the Yahoo designs and others, but most people are still using mechanical energy to dump their heat.
One of the things that we can provide as well is we put a sensor outside and monitor the temperature and humidity outside to determine when you can use your economizer.
Question here about how do we model swamp coolers. Again, a cooling unit is a cooling unit. From a CFD modeling point of view, it doesn't matter whether it's a swamp cooler or it's a craw or it's a crack or whatever it is, doesn't matter. All you need to do is define the airflow rate and the supply air temperature. When you're doing a design for any kind of economized system or swamp cooler or whatever, you're designing it based on the maximum supply air temperature, right? Because your goal as a design engineer is to keep that supply air temperature at or below a certain level. So from a modeling point of view, you model it at that design point, because anything colder is going to pass. Right? You can't be too cold in a data center. Although it falls out of the ASHRAE spec below 60 degrees, it's not as if the equipment's going to fall over and die. It might get a little brittle, but cold air isn't going to kill it. Hot air will kill it. So you want to model based on your maximum supply air temperature for a given case. And so for a swamp cooler, you just take a cooling device. You can use one of the standard cooling devices, or you can use the default cooling device. Just change its size, change its flow rates, and change its supply air temp, and use it. So it's very easy to do. Yeah, this one coming in saying, I just finished working on a design center design in New Jersey, and that's exactly what they did, and it reduced the chiller hours down by 8,000 hours a year. Yeah, let me point out that optimizing your data center for cooling can save a tremendous amount of energy. And remember that most data centers, for every dollar you put into the data center to drive the IT equipment, you're spending another dollar to get that heat out of the room. And every kilowatt that goes into that room, whether it goes in there as fan energy or goes in there as IT load, turns into heat and has to be pumped back out or dumped somehow. And if your dumping system, your heat rejection system, isn't operating at an efficient level, a COP of 4 or better with economizer, then you're going to be paying nearly twice for that kilowatt you're pumping into the room. So this is a very important topic, and the cost of the tools here that we're talking about to get a handle on this stuff is very low compared to the amount of energy and dollars that you're going to be saving if you optimize. Yep. So I guess that just about does it for questions. I don't.
One question here you didn't answer was the communications protocol between our gateway and other DCIM and other applications. And we can use SNMP, Modbus, TCP, ODBC, OPC, if any of those mean anything to you. So most of the standard protocols that that DCIM packages will support, we will deliver.
A question here with one last one. Does your application, Scott, tie directly into the CoolSim software? The answer there is no, not yet. We don't read the data directly. What I did is just took the data and entered it. It doesn't take very much. There's not very many entry points to take the data and enter it. But the idea of automatically reading sensor data to both set up and drive a CoolSim model is something that is quite straightforward and easy to do. If somebody wanted us to do that and was willing to purchase the software and the sensors for that purpose, I'm sure we would get that done. So not a tough thing to do. It's just reading data.
Very straightforward.
Yes.
Yeah. I did see one other question about interference with other RF systems, and because of the frequency hopping nature of our system, we don't interfere and we are not interfered with. So that fear it's an old fear, and it was well founded once, but with the kind of system we use, it's not a problem.
Okay. I think that just about concludes it. I'd like to thank everybody for attending. If you'd like a copy of the presentation or you'd like to see this reviewed, I do record these. It is being recorded now, and I'll put the recording up on our webpage. So go to coolsimsoftware.com, and you will see under archives, archived webinars, a whole list of them. This will be at the top as soon as I'm able to produce it, and that should be within about 24 hours. If you're interested in having us speak to you about the cost of this stuff, or having us do this for you, or teaching you how to do it so you can deliver to other people, please get a hold of myself or Scott, and we'll set up some training for you and get you started there. And finally, if any of you would like a certificate of education associated with this event, please send me a note and I'll produce one for you for 1 hour of credit associated with your professional development curriculum. So with that, I'd like to thank you, Scott, for attending today. I think that we laid out a process here that is a good one. I think that it is getting quite a bit of attention these days, this issue of how to take real-time data and combine it with simulation data to produce both a current state and a predictive model for future scenarios. It's a nice way to go, makes a lot of sense, and I know that we both support it.
Thank you, Paul. Nice job.
Yep, thank you, and have a good day.